This is called factorial design. Independent variable, not S. That means there is only one independent variable, right? But suppose you have two independent variables, then is your socioeconomic status and your school environment affects your achievement. And I am not only interested in your socioeconomic status, I am also interested in the school environment is affecting your scholastic achievement. Then there are two variables. They are independent variables. This example is not experimental, this was from survey method. But in experiment also you can have two independent variables and simultaneously you can employ them. You can give them tabs and you also can give them interactive material. Material can be given on paper also. So one independent variable is use of tabs. Another independent variable is interactivity in the learning material. And now you want to see the impact on the students' achievement. Then if you have more than one variable, we use factorial design. See here you can see this. There are two variables. On one side you will have tabs. What kind of tabs? What are they providing? What facilities are they providing? So you can have 1, 2, 3 types. And on this side, what is the level of interactivity? How interactive it is? You can have that. And then the scores. Low interactivity and high level, say Samsung tab, and see what is their achievement. High interactivity, and then you can see really whether both are impacting the achievement. Then we use factorial analysis where you get F ratio. The statistics which we get is F ratio. So F ratio for tabs, F ratio for interactivity, and third F ratio is for their interactivity. So you will get independent results for tab, you will get independent results for interactivity, and you will get results for interaction as well. So factorial design is also a true design, or it can be pre-experimental design. It depends on how you select your sample. But factorial design you have to keep in mind that more than one variables are attempted at a particular time. Now we go for quasi-experimental design. Non-randomized control group, there can be a control group, but they are non-randomized. Pre-test, post-test design. Another is counterbalance design. This is like the first one, pre-experimental, right? Counterbalance design. Counterbalance, countering means what? Changing. Rotation of groups at periodic intervals during experimentation. So it is also called rotation group design or crossover design. There are two groups, group 1 and group 2. Counterbalance means what we do? Group 1 gets treatment 1 first and group 2 gets treatment 2 first. Then what we do? Then we change. That means group 1 gets treatment 2 and group 2 gets treatment 1. And you get observations at every stage. After you give them treatment 1, you take it. Then you give them treatment 2, take it. And the difference between the two will really tell you whether the treatments are effective on any group, because these groups are having both the treatments. This also is done with single group. If you don't have two groups, then what do you do? The same group is used for one treatment. After some time, the same group is given another treatment. Suppose we are interested in collaborative, cooperative learning strategies. What are those strategies? We select two. Which one is more effective? We want to do that. But we don't have two groups. MIT says only one group. No? So what we do? First, one method is used. One topic is taught to that. Course and everything is there. Then after some time, same group is got with other. And then we see the difference. What was the achievement in both on the same group? See, we are controlling so many variables, right? So many variables are controlled. There is no control group. So that same people are doing it. There is no variability. Effect will be checked. See, treatment is given, no? So if I teach one topic through one method, collaborative method, say peer to peer, then I give you a test. So I have to score with me. Right? Then after 5 days or 6 days, another week, I use another strategy and teach you another topic. And again I get the score. So now there is a difference in your scores, right? First the average was 67, next the average was 76. So I say that the second treatment was better. They are not very happy with it. But it has to be done sometime. Why? There is only one group. Can you have another METCA group from somewhere? There is no METCA, you are the only people. So there are situations when we conduct experiments where you are not going to get more than one group. Not possible. So you have to use some other method. So it is an experiment, but it is not a true experiment. It is not like true experiment, because there you can really compare two groups where sample is randomized. But we have to conduct experimental design also we conduct. No single group experiment we conduct. We have no other alternative. We do that. You have to conduct. But then you cannot generalize. We say that the results cannot be generalized for everyone. So that is the shortcoming. It is a threat to your external validity. But knowing fully well, we say we don't want to generalize. Good enough. We say these findings are applicable to so and so. We are not saying all 8 standard students in the world. We are not saying that. So, as an experimenter, we know our drawback, our weaknesses, and then accordingly we say that there is a threat to external validity. Okay, the last design is called time series design. Time series. Series of measurements on dependent variables are taken before and after the treatment. I have to start the treatment after 1 month. So what I do, I start testing from today. I have 4 readings. Then actually I give the treatment and then again I test. One is called single group and other is control group time series. This is how it will look. It's not a pretest. Single group time series design. We are testing the same variable across. Right from 1, 2, 3, 4. I have 8 readings. But after 4 readings, I give the treatment. And then again I take 5th, 6th, 7th, 8th. It's a series of readings which I take. And I see, is there a difference in T1 and T2? Again, statistics use is different. Right now we are not discussing the statistics, but we are only saying, there is a difference in T1 and T2. Is there a difference in T2 and T3? Is there a difference in T3 and T4? Is there a difference in T4 and T5? There may be a big jump. Again, T5 and T6. So these readings over a period of time will give you another insight into the independent variable, a cause and effect relationship. If you have a control group, it would look like this. Instead of 1 group, it has 2 groups. So now you have 8 more readings, observations before you to see what is the trend in the difference. If you think of an experiment for this time series, where you have to test before, not one test, then treatment, and then again another. We are not interested in a cross section. So we stop here, no more going. It's not like that. If it is a continuous process, say attitude. So depending on the situation, depending on the resources which you have to select. But in that situation, you must select the best possible design. And you must know fully well why you have selected that design and what are the implications of that design. Because you must know what are the threats in this design. I would send you a link where that article is written only on this, because when you are writing about, you are preparing the write-up on various threats and valid threats for internal and external validity. I would suggest you take these experiments now. Suppose if you have taken maturity, then you will say on all 10, these are the 10 designs, how maturity impacts speed. Maturity would not affect the two designs because both the groups will mature if you have selected them randomly, isn't it? So maturity does not stand for true design. Like that, if you write why, giving the rationale, that would really make you aware about the design to be selected, to be used, so that whatever you do, ultimately we want to generalize. So to what extent you can generalize your findings. That also comes to one more issue. When you generalize something, you must have studied that when you test the hypothesis, have you studied the level of significance? When you test the null hypothesis, during the experimentation you must have had the null hypothesis. You will state there will be no significant difference before and after the treatment. But now there is a difference. Okay. Now here you will see there is a difference. Now with your crude eyes you can see the difference is 10. But is it because of chance? By fluke? Or if you conduct such 100 experiments, every time you will get the same result? You have to ensure that. Now you will ask me a question, are you telling us to conduct 100 such experiments? No. You can use statistics. Statistics seems to be answer for everything, right? There is a story of Ganesha and Kartikeya for taking pradakshina of the whole earth. Kartikeya bichara chala gaya. He went on round. But what Ganpati did? He took a round around his mother and he said, Mother Earth is same. So you don't have to conduct 100 experiments. You can use the statistics. Statistics will give you T ratio, F ratio, whatever statistics you use. That will tell you whether if you conduct this experiment 100 times, 99 times you will get the same result. It will also tell you if you conduct 100 experiments, 95 times you will get the same result. Then you can confidently accept that. One experiment is enough. Why enough? The statistics which you use, that gives you a confidence of rejecting the null hypothesis. What was that null hypothesis? There will be no significant difference in the pre and post test score. Now there is a difference and you are saying confidently that 99 times, if I conduct 100 experiments, 99 times I will get such difference. So the difference is a true difference. So my treatment was effective. If it comes 90 times, then we don't accept that. We are confident only when 95 or 99 times. Generally, in statistics, there are various confidence levels, but we generally accept only two confidence levels. One is 0.05 and another is 0.01, which means 95 times we are confident or 99 times we are confident. Okay. So one thing is, while selecting the experimental design, you have to be extra careful about various threats to internal and external validity, and other is while generalizing, you have to be careful to what extent you can generalize.